On January 28, 1986, 73 seconds after launch, the Space Shuttle Challenger broke apart over the Atlantic Ocean. 7 astronauts died. The whole world watched. I was not supposed to be part of the investigation. I am a theoretical physicist. I play with equations. I think about quarks and photons and the strange behavior of particles too small to see. I do not know anything about rockets. I do not know anything about space shuttles. I had never set foot inside NASA before that winter. But they asked me to join the Presidential Commission investigating the disaster. William Rogers, the chairman, a former Secretary of State, he put together a group of generals and astronauts and politicians and engineers. And for some reason, he wanted a physicist from Caltech who knew nothing about the shuttle program. Maybe that was the point. Maybe they wanted someone who would ask stupid questions, someone who had no relationships to protect, someone who did not know which doors were supposed to stay closed. I said yes, and what I found in the following weeks changed everything I believed about how organizations work, how disasters happen, and how the people in charge lie to themselves even more than they lied to everyone else. Let me tell you what really happened to Challenger. Not the official story, not the sanitized version. The truth that NASA did not want anyone to know. The morning of the launch was cold, unusually cold for Florida. The temperature at the launch pad was 36 degrees Fahrenheit. That is just above freezing. Ice had formed on the launch structure overnight. Icicles were hanging from the tower. This mattered enormously, but the people making the decisions did not understand why. The space shuttle used 2 solid rocket boosters to help lift it off the pad. These boosters were made in segments, manufactured in Utah by a company called Morton Thiokol, then shipped by rail to Florida and assembled. Where the segments joined together, there were gaps. And to seal those gaps, to keep the hot gases from escaping during the burn, there were rubber rings called O-rings, simple rubber rings, like the gasket in your sink, like the seal on a jar. Nothing exotic, just rubber pressed into a groove designed to expand and fill the gap when pressure built up inside the booster. The night before the launch, engineers at Morton Thiokol held a teleconference with NASA managers. They were worried. They had data showing that the O-rings did not perform well in cold weather. At low temperatures, the rubber became stiff. It lost its flexibility. It could not expand fast enough to seal the gap when the booster ignited. They had seen evidence of this on previous flights. On missions that launched in cooler weather, inspection of the recovered boosters showed damage to the O-rings. Hot gases had begun to eat through them. They called this blow-by. The seal was failing. Not completely, not catastrophically, but failing. The coldest previous launch had been at 53 degrees, and that launch had shown the worst O-ring damage they had ever seen. Now they were being asked to launch at 36 degrees, 20 degrees colder than anything they had ever attempted. The Thiokol engineers said no. They recommended against launch. They said it was too dangerous. They said they could not guarantee the O-rings would work. And then something happened that I still find hard to believe. NASA pushed back. The NASA managers on the call did not say thank you for the warning. They did not say safety first. They said, when do you want us to launch next April? They said, my God, Thiokol, when do you want me to launch next year? They were irritated. They were impatient. They had been dealing with delay after delay. The shuttle program was under pressure to prove it could launch on schedule reliably like an airline. And the Thiokol engineers, the ones who knew the data, the ones who had done the analysis, they were overruled by their own management. After a 30-minute recess, Thiokol management came back on the line and reversed the recommendation. They approved the launch. One of the senior managers later testified that he was told to take off his engineering hat and put on his management hat. Take off your engineering hat. Think about what that means. Stop thinking about physics. Stop thinking about data. Stop thinking about the rubber and the cold and the blow-by. Start thinking about schedules. Start thinking about contracts. Start thinking about what NASA wants to hear. The next morning, Challenger launched. 73 seconds later, hot gas burned through the O-ring, escaped from the side of the right booster, and hit the external fuel tank. The tank ruptured. The shuttle broke apart. 7 people died, and everyone in that teleconference knew it was going to happen. When I arrived in Washington to join the commission, I did not know any of this. Nobody told me about the teleconference. Nobody told me about the O-rings. Nobody told me that engineers had begged not to launch and been ignored. The commission was holding formal hearings. Witnesses in suits, prepared statements, lawyers whispering in ears, everything very polite, very controlled, very slow. We were scheduled to produce a report in 4 months. At the rate we were going, I thought we would learn nothing. I do not work that way. I never have. When I want to understand something, I do not sit in a conference room listening to officials read prepared remarks. I go find the people who actually do the work, the engineers, the technicians, the ones with grease on their hands and data in their notebooks. So I started wandering, I started asking questions, I started showing up at NASA facilities unannounced, talking to anyone who would talk to me. And what I found shocked me. The engineers knew, not just the Thiokol engineers, NASA's own engineers. They knew the O-rings were a problem. They had known for years. There were memos, there were reports, there were presentations with titles like "Help" sent up the chain of command, warning that the seal design was flawed and that they were flying with an unacceptable risk, and nothing had been done. The warnings went up, they hit management, and they stopped. They were absorbed into the bureaucracy like sound into a padded room. The managers acknowledged the concerns, scheduled more meetings, commissioned more studies, and kept flying. One engineer told me something I will never forget. He said that NASA had developed a peculiar way of thinking. When they flew a mission and the O-rings showed damage, but the shuttle did not explode, they did not say we got lucky. They said the damage was within acceptable limits. And the next time there was more damage, they expanded the limits of what was acceptable. They kept redefining success until failure became invisible. This is what I call playing Russian roulette. You spin the chamber, you pull the trigger, the gun does not fire, and you conclude that the gun is safe, but the bullet is still in there. It did not go anywhere. You just got lucky. And every time you pull the trigger again, you are betting that your luck will hold. NASA had been pulling the trigger for years, and on January 28, 1986, their luck ran out. I wanted to understand the physics myself. I wanted to see it with my own eyes. So I asked for data. I asked for test results. I asked what happens to the O-ring rubber at low temperatures. The answers were scattered. Nobody had a clear picture. So I went to a hardware store in Washington. I bought a small clamp. I bought a pair of pliers. and I obtained a sample of the actual O-ring material, the same rubber compound used in the shuttle boosters. The commission was scheduled for a public hearing. Cameras everywhere, the whole country watching, and I had an idea. I asked someone to bring me a glass of ice water. During the hearing, while the NASA officials were giving their careful, rehearsed testimony, I did a simple experiment. I took the O-ring material, compressed it with my clamp, and dropped it into the ice water. I left it there for a few minutes, letting it cool down to 32 degrees. Then I removed the clamp. The rubber did not spring back. It just sat there, compressed, stiff, unable to expand. At that temperature, the material had lost its resilience. It could not seal anything. It could not do its job. I held it up and showed it to the cameras. That was the moment. That was when everyone understood, not from charts and graphs and technical testimony, from a simple demonstration that anyone could see. The rubber did not work in the cold. The engineers had said so. The data had said so. And now a glass of ice water said so. The O-rings failed because they were frozen, and NASA launched anyway. But here is what really disturbed me. Here is what kept me awake at night long after the hearings ended. It was not the O-rings. Hardware fails, rubber gets cold, seals break. These things happen. You design around them, you test for them, you build in margins of safety. What disturbed me was the lying. Not lying in the simple sense, not people deliberately saying false things, though there was some of that too. A deeper kind of lying, a lying that the liars themselves did not recognize. NASA had calculated the probability of shuttle failure. They had a number. They told Congress, they told the astronauts, they told the public that the chance of a catastrophic accident was about 1 in 100,000. One flight in 100,000 would end in disaster. Those were the official odds. I could not believe this number. It made no sense to me. So I started asking how they had calculated it, and I discovered that they had not calculated it. Not really. They had started with the conclusion they wanted and worked backwards. They needed the shuttle to seem safe enough to carry civilians, to carry a teacher into space for a public relations event. So they needed a very small probability of failure. And they found ways to justify whatever number they needed. When I did my own calculation, when I talked to the working engineers and asked them what they really thought, the number I got was around 1 in 100. Not 1 in 100,000, 1 in 100. 1,000 times more dangerous than NASA was claiming. 1 in 100. That means if you fly 100 missions, you expect to lose one. The shuttle had already flown 25 missions. They were a quarter of the way to a disaster, and the people at the top either did not know this or did not want to know it. Let me tell you what I concluded from all of this, because it is not just about NASA. It is not just about the shuttle. It is about how human beings deceive themselves, how organizations become blind to their own failures, how the people in charge can be the last ones to understand what is really happening. At the top of NASA, there were managers who believed the shuttle was safe. They believed it sincerely. They were not villains. They were not monsters. They were people who had stopped asking questions. They had stopped listening to the engineers who were trying to warn them. They had built a system where bad news got filtered out on its way up the chain. The engineers at the bottom knew the truth. They knew the O-rings were dangerous. They knew the probability of failure was far higher than management claimed. They wrote memos. They raised concerns. They argued in meetings. But by the time their warnings reached the top, the warnings had been softened, reinterpreted, turned into acceptable risks. This is what happens in organizations that punish bad news. People learn to stop delivering bad news. They learn to phrase things carefully. They learn to cover themselves with paperwork while letting the problem continue. And the people at the top, the ones who need accurate information the most, end up knowing the least. I call this the disease of management. The higher you go, the less you know. The more power you have, the more people tell you what you want to hear, until eventually you are making life and death decisions based on fairy tales. When it came time to write the final report, I had a problem. The commission wanted a clean report, a unanimous report, a report that criticized NASA but not too harshly, a report that would recommend improvements but not embarrass anyone too badly. They wanted consensus. I could not give them consensus. What I had found was not a technical failure. It was a failure of thought, a failure of honesty, a failure that went to the very top of the organization, and I was not willing to pretend otherwise. So I wrote my own appendix, my own personal observations on the reliability of the shuttle. I submitted it separately from the main report, and I told Chairman Rogers that if my appendix was not included, I would hold my own press conference and release it myself. They included it. In that appendix, I wrote something that I think is the most important conclusion of the entire investigation. Let me read it to you exactly as I wrote it. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. That is the lesson. That is what Challenger taught us. You can fool Congress. You can fool the press. You can fool the public. You can even fool yourself. But you cannot fool nature. You cannot fool physics. You cannot fool the rubber in an O-ring when it is 36 degrees outside. Nature does not care about your schedule. Nature does not care about your budget. Nature does not care about your public relations or your political pressure or your management philosophy. Nature only cares about reality. And if you ignore reality, nature will kill you. 7 people learned that lesson on January 28th, 1986. They learned it in the last 73 seconds of their lives. After Challenger, NASA changed. They redesigned the boosters. They added a 3rd O-ring. They improved their communication between engineers and management. They said they had learned their lesson. And then 17 years later, it happened again. On February 1st, 2003, the Space Shuttle Columbia broke apart during re-entry. 7 more astronauts died. The cause was different. Foam insulation from the external tank had struck the wing during launch, damaging the heat shield. When Columbia re-entered the atmosphere, hot gases penetrated the damaged wing and the shuttle disintegrated. And when investigators looked into what had happened, they found the same patterns. Engineers had warned about the foam strikes for years. Management had dismissed the concerns. The same disease, the same filters preventing bad news from reaching the top, the same Russian roulette. They had learned nothing. Or rather, they had learned and then forgotten. The people who remembered Challenger had retired or moved on. New managers had come in. New pressures had built up. And slowly, gradually, the organization had drifted back into the same habits of thought that had killed 7 people in 1986. This is the terrifying thing about institutional failure. It is not a one-time event. It is a tendency. It is a way of thinking that emerges whenever an organization faces pressure to succeed, pressure to perform, pressure to tell good news instead of truth. I think about this often. I think about those 7 astronauts who climbed into Challenger that cold morning. Krista McAuliffe, the teacher, who was going to broadcast lessons from space. Gregory Jarvis, Judith Resnick, Ronald McNair, Ellison Onizuka, Michael Smith, Francis Scobie, 7 human beings who trusted the people above them to make good decisions. They trusted NASA. They trusted the engineers. They trusted the managers. They trusted the system, and the system killed them, not through malice, not through incompetence, through something more subtle, through the slow erosion of honesty, through the gradual acceptance of risk, through the quiet silencing of the people who knew the truth. I am a physicist. I have spent my life trying to understand how nature works. And what I learned from Challenger is that the hardest thing to understand is not nature. It is human beings. It is how we think. It is how we lie to ourselves. It is how organizations become blind to reality, even when reality is screaming at them. Nature cannot be fooled, but we can be. We fool ourselves every day. We ignore what we do not want to see. We believe what we want to believe. We take off our engineering hats and put on our management hats, and we convince ourselves that everything will be fine. And sometimes, 73 seconds after launch, nature reminds us that we are not as smart as we think. 7 people died because the rubber was too cold. 7 people died because the engineers were not heard. 7 people died because the managers believed their own lies. And that is what NASA hid, not the O-rings. Everyone found out about the O-rings eventually. What they hid, what they never wanted to admit, was that they knew the risk. They knew the warnings. They knew, and they launched anyway. That is the truth I discovered, and it still haunts me.